All right. Hi, everyone. So while everyone is sitting down, there is a quiz. Please go on Quarkus. We're doing the quiz for a couple of minutes. And this time I'm pretty sure there. Do you have the quiz on Quarkus now? Does anyone see the quiz? All right. Hi, people coming in. There's a quiz. Sit down, do the quiz, please. All right, so we actually have an observer in this lecture, so to explain to Arthur what's going on. So we occasionally have those quizzes. They usually work on Quarkus. Those are mostly used to just encourage people to attend lecture as opposed to evaluate people. We sometimes try to ask questions that would be useful during the lecture, as is the case today. So to recap, what's log 2 1032? So that's just a useful thing that you should remember for, well, maybe not necessarily this class, but certainly for job interviews, people do like to check that you know this. And what you should know is that 10 to the third is approximately equal to 2 to the power of 10. And 10 to the third, you hopefully know, is 1,000. So that means that log 2 of 1032, which means to what power should you raise 2 so as to get 1032? The answer is 10. So here, just because of this pattern that 10 to 10 cubed is 2 to the 10, you can infer what is the log 2 of any number by just remembering, oh, this is just 1,000 squared, right? So 1 million is equal to 1,000 squared. So that means that that's equal to 10 cubed to the power of 2. So that means that it's equal to 2 to the 10 to the power of 2. The way powers work is 2 to the 10 to the power of 2 is 2 to the power of 20. So if 1 million is approximately 2 to the power of 20, that means that log to a million is equal to 20. All right. So the general pattern, and that has to do with dropping the base of the logarithm when you're computing the logarithm. The general pattern is like that. So what's log 2 of n? Well, that's equal to, just because that's how logarithms work, that's equal to log 10 of n divided by log 10 of 2. right? So the pattern is, if you know log 10 of n, you also know log 2 of n because the difference is just log 10 2, right? So what does this mean in particular? Well, that means that log 2 of 1 million is log 10 of 1 million, which is 6, divided by this constant log 10 2. So you can compute log 10 2, that's just a number, that's kind of to what power should you raise 2 so that you get 10. So it's a little bit more than 3 because 2 to the 3 is 8. So you can compute it again by saying math log 10 divided by math log 2. And it's like 3 points. Okay. So that's kind of how it works. Okay. So sorry. So of course this is like log 10 divided by log 2. So that's what you multiply by, right? Because log 10 2. So basically you can multiply 6 by 3.32 and you get the bottom line. So for that reason, when we say so for that reason, so to be explicit about that, that is equal to 1 divided by log n of 2. So for that reason, when we say it's O of log 2n, that's the same as saying O of log n. Why is that? Well, it's because log n, whatever base it is, differs from log 2n by just a multiplicative constant. And we don't care about multiplicative constants. Does that make sense? So, okay. So, and again, kind of another callback to last time's lecture. What we had is we said like kind of how many iterations to run binary search on a list of length 1000. And the answer is, well, it was log 2 1 million approximately. So what's log 2 1 million? Well, it's about 20. How do you know? You can even compute it by hand because you know that log 2 1 million is just 6 times 3.3, which is approximately 20. When we write in big O notation, we don't care about the multiplicative constants. We just say binary search is O of log n. Are there questions about this? People who are coming in late, there is a quiz, which is due, I believe, at 4:30. So you should probably do it. The answer are here. Yes. So I think because they're proportional. So for any base b, log b1n is equal to some kind of c times log b2n. That's because you can change the base like this, and you see that what you need to do is you need to just divide by log b1, b2. Well, so that's the other thing that that I was gonna bring up just now. So what do we care about when we are doing complexity analysis? So let's just review quickly. So if you have something like this, then in general, how many iterations? Well, that's easy, right? So K1 times K2 iterations. Do we always just care about the number of iterations? Well, yes, as long as the something here takes time that's constant, right? Because at the end of the day, what we care about, like when we're asking what's the runtime complexity, we're asking what's the runtime proportional to. If what's happening inside the iteration is the same amount of time every time, you can just ask how many iterations, and then the runtime would be the time it takes to do something times K1, K2. On the other hand, and that's the example that we ended with last time, it might be that the something there doesn't actually take a constant amount of time, right? So the example that we had, that's what happened kind of at the very end of the lecture. The example that we had was kind of like this. We said like A is equal to 10. And then we just multiplied A by 10 by whatever, 20 every time. So that looks like it takes a constant amount of time, but it doesn't. The reason it doesn't is that as A grows larger and larger, if it's an integer, it could have an unlimited number of digits. Multiplying it by something takes more and more time because you need to store more and more digits. So that's an example of a situation where the analysis is actually quite complicated. Now, you can make it very easy by just doing this. And the reason is, like we saw in the midterm, a float is different from an integer in that takes constant time to do a multiplication. It doesn't matter what the value of A is. And that's because a float has a constant number of digits. It might grow too large, then it might crash, but it's not going to take more and more time as A grows. And that's because an integer is unlimited. You can have a very large integer that takes a long time to store. With floats, it doesn't work like that. So for that reason, on the exam, you'll see on the recent exams, once we switch to Python 3, where this is an issue, you'll notice that I always use floats, never integers. And that's because someone can come to me and say, oh, like, actually, there is this complicated thing with integers where they can grow very large, and your supposed answer for what the complexity is incorrect. Now, with floats, there is a different problem, which is that they're limited in size. So someone might come to me, and please don't do this, but someone might come to me and say, well, like, you run this for a large enough float, it's just going to crash. That means that the complexity is of 1 because it always crashes in a set amount of time. So that's limited. So there are, is that understood? So it might be that this float might get too large depending on the settings. If the float gets too large, it just says, I cannot store that. Yeah. It will. Yeah, so float operations are constant. Int operations, not necessarily. So like obviously kind of the other kind of joke, and I think I mentioned it before, but it's Friday, I might just as well tell you, don't tell it to me back on the exam, it's not that funny. But the other kind of thing that you could say is, well, a computer's memory is finite. If a computer's memory is finite, that means that there is only so many things that could be stored differently in memory, right? So like imagine like every bit, it could be 0, it could be 1, where there's a finite number of settings there. So what does it mean for complexity analysis if you're analyzing the complexity for n going to infinity on any computer? Well, it means that one of two things are going to happen. One possible thing that's going to happen is the memory it's going to stop, and it's going to stop before cycling through all the possible configuration of the memory. The other possible thing that could happen is, you know, one bit changes, another bit changes, another bit changes, and eventually the computer comes back to exactly the state that it was before. Well, if everything in the computer is exactly the same as it was before, that means it's in an infinite loop because it's just going to go around and around. So technically for any computer with finite memory, because of this, either it's an infinite loop or it crashes or it stops, which means it's kind of fault one. Please don't say that on the exam either, even though it's completely true. Okay, so when we're analyzing for complexity, we are making compromises. You cannot assume the top integer operations are constant. They really are not. On the other hand, everything else you assume is constant. And if you have a constant number of operations here, all you need to do is you need to just say how many iterations. So in general, so what we do is we identify what we're counting. And generally, it could be operations like we've done in the first time we did it, or we could say iterations, assuming every iteration takes the same amount of time. Or it could be a particular kind of operation. So very frequently in textbooks, you'll see you're just counting the comparisons. So for example, comparisons, assuming that the number of comparisons is proportional to the runtime. So that's the same thing, right? So here, why would you be counting iterations? Well, because you're saying, well, every iteration takes the same amount of time, so the total runtime is going to be proportional to the number of operations. So write down the formula for the thing you're counting. And then simplify. Right? So here, for example, we're saying, okay, this is the thing that we are repeating. Let's count how many times we repeat this thing. So let's count how many times we have an iteration of the inner loop, essentially. Or you could say, how many multiplications are we doing? We make sure that the number of the times 20 is actually proportional to the runtime. How do we do that? We say, well, float multiplications take the same amount of time every time. It doesn't matter what the value of the float is, approximately. And then we say, yes, like we're doing other stuff here. So J keeps increasing and I keeps increasing. But really, the number of times that J increases is the same number of times that we multiply A by 20. And yes, I sometimes increases, but the number of times that I increases is much smaller than the number of times that J increases, so we don't care. Because the runtime for doing I is 0, 1, 2, and so on up to K1 minus 1. Well, that just happens K1 times. On the other hand, this thing happens K1 times K2 times, so always much larger. And then we say, okay, what's the formula here? So the formula would be K1 times K2 iterations. And then in big O notation, it would be O of K1 times K2. All right. So the reason this is this probably feels a little bit vague. Like, are you counting operations? Are you counting iterations? The problem is it's very difficult to specify exactly what you're supposed to be counting because it might even be different in different computers. It's very difficult to look at Python code and identify exactly how many operations each thing is. So you have to approximate a little bit. So in practice, sometimes weird things happen, right? So one weird thing that they mentioned was, oh, actually, like integer multiplication can take longer for larger integers. So that could happen. And that's one thing that you need to know about. There are things that might happen that you would not necessarily be aware of. And for ESC180 purposes, it's fine. So when you're doing ESC190, you'll have kind of more details about what's going on in the computer. So you have like a little bit more insight. But generally, this kind of process just works. Yes. Yeah, that's a good question. So if K1, so the question is if K1 and K2 are actually constants and will never change, then what is it? And the answer is, well, if K1 and K2 are constant and it will never change, the thing takes a constant amount of time. So it's O1, or you could say, oh, K1, K2, but if it happens that K1 is 5 and K2 is 3, then O15 is nothing, it's O1. Right? But it also doesn't hurt to write it as, oh, K1 times K2, just in case it happens that K1 and K2 happen after all to not be constants. So just to be safe. Okay, does that make sense? Questions? All right, so that was kind of a little bit philosophical. So far what we had was linear search, which you remember was go through the list of length n and compare each element to the query. That was O of n. And then we had binary search, and that was O of log n. And I want to give a few more algorithms so that you get more of a feel, well, real algorithms rather than toy algorithms, so that you get more of a feel for what can happen. So there is a question on the Discord. Uh, 1024, was it not 1024? Oh, yeah, that really should be. Yeah, okay. So here's the problem that they want to solve, and it's actually a little bit relevant to the project that you're working on if you're still working on it. So thanks for coming to lecture. That's my free gift to you, although you don't need it for the project. So let's say that what I want to do is I want to figure out what's the longest sequence consisting of A's in a string S. So for example, if S is like A, B, A, B, A, or something, and then like X, whatever, then the longest sequence of A's is 5. So what I'm going to do is I'm going to write a slow algorithm first, and then I'm going to try to write a faster one. So what can you do that's like very fast? You can say, okay, I'm just not going to try very hard. I'm just going to do the same thing that I kind of nudged you towards in the project. Let's check if there are length of S A's in there. If there are, we're done. Let's check if there are length of S minus 1, and so on. So in Python, sorry, I know it's Friday evening, but thank you. I don't have my glasses today, so I can't really call out people in the back, but you know who you are. So what you can do in Python, if you remember, is you can do this multiplication trick. So that would be 5 A's. And you can also do something like this. So like ABC in ABCDE, that's going to be true. And ABC, hey. Yeah, so so people, one of piece of feedback that we got is that like people in the back can't always hear. So please communicate by text if you have to. And ABCQ would be not an ABCD, so that's false. So what I'm gonna do is I'm just gonna say, okay, let's try the longest possible sequence of A's and see if it's in the string, and then the second longest and so on. So I'll start with length of S minus one, sorry, length of X actually. And then I'll go down to minus one in steps of minus one. And I'll say, so if A times length is an S, I'll return length. And if I haven't found anything, I'll return zero. So why did it do it this way? So what would happen if I started with zero and went up the length of S? Anyone? Yeah. Yeah, which is zero, yeah. So I'll just get out because like if I check first if A times zero or A times one is an S, well, if it is, I'll return right away. What I want is I want to return the longest one, so I check the longest one first, and then I go down to the second longest possible, and so on. And so if I have something that's of length of S, I return that right away. I have something that's of length of S minus one, I return that, and so on. Yeah. What? Which author? Sorry, that's like not about this. Select Discord, please. Okay. So okay, yeah, like random trivia question. So yeah, anyway, so okay. So we're doing this like this. So what's the runtime complexity here? So this is one of those situations where it's a little bit misleading because you might say, well, there is one loop, it goes length of S times, looks like all length of S. Well, no. One of the reasons that's not the case is if you think about what it takes for the computer to just construct this A times length string. Well, it's got to be that if length is very large, then A times length would take more time because you literally need like length A's to be stored in memory for this. If you need to store a lot of A's in memory, well, that would take more time. So what's the complexity of this? Well, not O of length of S. So by the way, you can write O, so it's not that anyway, but you can write O of length of S, or you could write like O of N, where N is equal to length of S. It's always important that the input here actually makes sense. So if I write it as O of N, then I specify that by N, I mean length of S. But anyway, it's not that. And the reason it's not that is that it must be, at the very least, that this doesn't take a constant amount of time. It takes more time the larger length is. So there is another problem, which is, well, like, let's say you construct this guy. How long is this operation taking? So how long does it take to check whether A times length is really an S? Well, don't know. So what I'll do, and that's the usual thing, you can't always check because in Python, you don't necessarily know how things are implemented. What I'll do is I'll just rewrite it in a way that would be easier to analyze. So just write something that's kind of equivalent. And by the way, so if you're asking, like, if this appears on the exam, what do I say, given that you just said that it's not O of N? Well, if I give you a true-false question that says, is it O of N for N equals length of S, the correct answer is no. But how do you analyze it? Well, you can't analyze it without more details about how the Python programming language works, which is not even necessarily specified in the Python documentation. It might be different for different versions. So the answer is, well, more than O of n, but hard to say how much. So what I'll do is I'll just implement something that makes kind of for an easier analysis. So I'll still do this. And here I'll just call a function that checks whether there are length times A's in S. Then I'll return length. Otherwise, I'll return 0. So now I need to write an A's in S. So this is like this. So that'll take S, and it'll take N. And now I just need to check whether there are N of those A's in S. How would I do it? Well, one way to do it is I just go through S and I say, so far I have this many A's. If I encounter an on A, I reset the counter. If I get a new A, I start the counter again. So I'll say counter initially is 0. And I'll say for letter in S. So if the letter is A, I'll increment the counter. If the letter is not A, then I'll say, okay, like how much is my counter? Is that larger than what I've seen so far? So initially max counter is going to be 0, and I'll say if counter is greater than max counter, say max counter is counter. So there is a small bug here that I'll fix in a second. So what does it do basically? So basically what happens is, let's say that you have this kind of S. We start with counter at 0 and max counter 0. And now what we do is, okay, we encounter an A. Okay, that's an A, increment the counter by 1. Now we're at the B. Well, that's a not A, so the sequence of A's just ended. So the largest sequence of A that we saw so far is of length 1. So, okay, that's the largest that we saw so far. Now we have an A, and the counter becomes 0 again. So now we have another A, okay, counter is 1. Another A, counter is 2. Another A, counter is 3, 4, 5, counter is now 5. And now we're at the B, so the current sequence of A has ended. So now we'll again say, okay, cool. So max counter is 5, and counter is again 0. And now counter is 1, 2. Again, the sequence has ended. Is counter greater than max counter? No, we already saw a sequence that's larger. Okay, fine. Just reset counter to 0. Is that an A? No. So is counter greater than max counter? No, it's 0. And then we're done. And at the end, we return max counter. Right? So that's something that you can use in project 2 if you wanted to. If you want to, so we'll improve it more if we have the time. But that's the same kind of idea that you can use in order to count, for example, the number of X's, the number of W's and D's on the list. Another connection that I want to make here is this is kind of a little bit like project 1. This is a little bit like project 1 in the sense that you keep getting inputs. So you keep getting a new letter. And as you get a new letter, you update your state. You update the counter and you update max counter. So it's kind of like in this case, you're just getting the next character from the string. but it's kind of the same style as project one. And that's a very common thing. So we won't get into detail, but that's an example of what's called a finite state machine. And this is kind of more like second year theory, but the idea is basically you keep getting input and you keep updating the state. So that's something you saw in project one and something that you see again. Does anyone see a bug in this implementation? Yes. Exactly. So what if you have something like this? Well, you never get the chance to update the max counter, right? Because you go like counter is whatever this is, and then the loop just ends and you return the previous max counter because this sequence has never ended. So there's various ways to fix this. So I'll resort to kind of a vandalism here and fix it like this. Now S never ends with me because it ends with me. Okay, so I mean, I think arguably the most elegant thing. Does that make sense? Questions? So, okay. So we have this, and now we have a full implementation of a thing that kind of looks like what we've written about. So what's the runtime complexity of this? Well, the answer is, again, not all of length S. Well, obviously not all of length S, because this is going to take different amounts of time, possibly every time, right? So in fact, how much is this going to take? Well, the runtime of this is going to be what? Well, you just need to run this length of S times, right? So that means that this part takes A is taken, so C times length of S operations, right? So what's C? Well, C would be the number of operations per this block of code. Because what's going on is we're calling an A's in S, and we are repeating this length of S times. So how many operations? Well, C times length of S. How much time? Well, C1 times length of S for whatever is the conversion factor. Yes. Sorry, can you speak up, please? Oh, we never use it. It's true. Yeah, so I meant for this to be kind of a worse function than it is. I meant max counter is equal to X, but I meant. Thank you. So I need to check whether there are, in fact, sorry. So I'll break this function. Yeah, sorry, that's a good point. That was like a better function than I meant. So what I meant to say is every time I'll just check if counter is equal to N, and I'll return true. And I'll remove that later. Yes, thank you. Does that make sense? So this is actually kind of a better function than it used to be. So right now I'm just breaking it, and I'll just return true if counter is equal to N at any point. And here I'll just return false because I never returned true. Thank you. So, okay. So the analysis though still holds because I might never return true. So what's the complexity of that? Well, I'll repeat this length of S times. It takes C operations, or if you like, C seconds. So the runtime is going to be proportional. Yeah. Oh, well, I'll fix it. Like this function is better than it looks. So we'll fix it later to be better. All right. But the answer is currently no, max counter is not doing anything. So, okay. So we're doing it like this, and this is kind of parallel to what we've done before. What's Discord saying? Are they correcting? I'm assuming, well, I don't need a lot of things there, but I'll need them in a second. I'm sorry, I got a little bit ahead of myself. So, okay. So this is C times length of S operations, and then we repeat length of S times. So that means that in total, in the worst case, C times length of S squared operations, approximately. So O of N squared, or N equals length of S. Yes. So C would be the number of operations here, right? Because what we're saying is, in the worst case, if we don't return early, so if we never get to this return true, what's going to happen? Well, this guy is going to run length of S times. So if it takes C operations, then in total, it's going to take about C times length of S operations. So the reason I kind of slid back to operations is that I needed to express this somehow. And sometimes people say, oh, that's O of N. Well, that can be misleading. It's better to write it down as operations. And that's because if for different amounts, it's going to be like different multiplicative constants, the multiplication is not going to work. Okay, does this make sense? Questions? Sorry, quiet answer. All right, if you have a question, speak up. If not, no, yes. Lots. So right now, everything is necessary except some of the variables there. But we'll, so this is kind of getting ahead of us just a little bit. I'll improve the function in a second. But does this make sense, except for things that are maybe not necessary? Questions? Yes. Yeah. If Python functions are big, so big O notation is a way to express what is the runtime proportional to, right? So the runtime of any Python function is proportional to something. You don't always necessarily know what. Does that answer the question? Which example? Sorry, where? Oh, this? O of length. Well, so this is really a question about like, can I use, so like big O is a mathematical construct, right? So your question is, can I like write math with Python? And the answer is sure. Now, sometimes the situation is, in fact, like with the lab, right? I had you actually write a Python function that returns the number of iterations. So in principle, like if you're asking like on the exam, can I do that? Well, you might get around any question about complexity by just modifying the function such that it counts the number of iterations, which is usually not difficult. And then just plug that in as your answer. And that's creative, but I thought of it first, so you can do that. In general, kind of, I think you're asking because I used length, and I think length is legitimate. Kind of range, I think, is questionable. Like if you don't know how to add all those things up and you're trying to get away with it, like it's basically sigma, except you rewritten it in Python, right? Yeah. So, well, no, like you got to be able to do the math. Is the answer. Of course, kind of that's for the exam. In general, in life, well, sometimes there is no formula for this. Yeah.
Is it safe that only for n is before
No, not really. Like nothing is safe to assume. Sometimes the answer is you just can't tell. So I think you're at, sorry, give me, guys, 4 more minutes of quiet, please. Again, I would like to point out we could have so many more quizzes if I didn't have to stop you all the time. That would be fun for everyone. Yes.
yeah, so the runtime for n is before
So the answer is sometimes it's difficult to tell. So something like that. I mean, like the answer is not necessary. So the answer is basically basically it's more squared than a big O of n, because if you're asking like is ABC in something like this, well, it's so like there is an O of n algorithm, it's unclear that it would be executed. You shouldn't be assuming stuff.
so n is
Yeah. Well, so here we're not assuming, right? We are like actually analyzing.
so yeah, so is that just n?
Well, I mean, so it's not exactly n, it's length of s. So this is actually a good example in that n and length of s are different, right? So this is O of length of s, but not O of n because n is something else. You could, of course, always say like O of k, where k is equal to length of s, or I suppose you could redefine n or something. But yeah. So, okay. All right. So this is length of s squared. So now in the 2 minutes that are left, I can actually fix it so that it's O of n. And that's because this function can actually be fixed to return the number of A's in S, because you can always just return max counter. And that just gives you the answer to the question. What's the complexity of this? Well, O of length of S. So here you have, so here you don't have best case, worst case, because you always return max counter. You always run this length of S times. This is as opposed to here where you could have an early return. So in the worst case, this is O of length of S. But best case is not. So best case is O of 1 because in the best case, you just see an A right away and n is equal to 1 and you return true. Make sense? So the upshot is that this, which you might or might not have thought of, kind of looks like it's O of n squared, where n is length of S. On the other hand, something like this, which does the same task, is O of n. So the upshot is there are efficient and non-efficient algorithms. Write the efficient ones. I'll see you on Monday. Thank you. And office hours, whenever announced, I think 5:30 and a SAP 10:13, and then there's some on Saturdays as well. Yeah.